Okay, so today we're going to do our Chapter 11 review. I already started making a video, but the lighting is kind of weird, so I stopped to try to fix it. But I think this is going to be a little bit better. So it's mostly a Chapter 11 review. There's a little bit of ochem 1 review in there as well. But the majority of what we're covering today is going to be Chapter 11. Okay, so there's a diagram of the ways to make alcohols. You can do that however makes sense to you, but the big things to get is 3 ways to add water across a double bond. So that would be the oxymercuration, demercuration, the hydroboration, oxidation, and the acid catalyzed. So you start with a double bond and you do an addition reaction to add H on one side and OH on the other. There's also 2 ways to make diols. And then you can do an SN2 reaction with OH minus as the attacking group. And those are kind of the biggest ones that it's important for you to remember from Chapter 11. And then draw a diagram of all the ways to make ethers. There are 3 main ones. That would be Williamson ether, which is basically just an SN2. There's symmetrical acid catalyzed. And when you're doing these, I would go ahead and write in all of the reagents and stuff like that, but we do want you to do it on your own just so that you're working to make a study sheet for yourself, because that will actually help put it in your brain better. And then you can do asymmetrical acid catalyzed. That goes by SN1 mechanism, but it really only works with the tertiary because then it has to make that good carbocation. And then you can also make them you can make an epoxide, so using MCPBA or another peroxy acid. And peroxy acids are those ones that basically look like confused carboxylic acids. And then what reactions could you use to react alcohols and ethers forward? Some big ones, if you have a primary or secondary alcohol, you can use PBr3 to make it into a better leaving group. You can use SOCl2, so that makes it into a primary or secondary, whatever you start with, alkyl halide, specifically bromine. Same thing here, primary or secondary alkyl chloride. You can use an SN1 reaction. And that's really with primary, secondary, tertiary alcohols. You can do that as the nucleophile. And you can protonate it to make it a better leaving group. You can also do an epoxide ring opening with an ether. You only had to write 4. Dr. Corrales said you only have to write 4, but if you want to do more, that's fine too. I'm going to try to make this a little bit bigger for you. Okay. And then in addition to the epoxide ring opening, you could also do, that's acid or base catalyzed, and we'll talk about that more in another video. You can also do a cleavage of ethers with HBr or another HX. So those are just some reactions you can do with alcohols and ethers, but there's definitely ones I missed, and I'm sure you guys put other ones that are also valid. Okay, for this one, all of the ring opening of epoxide stuff, I'm actually just going to do this on a separate video because I think it's going to take a while, and I'll be posting that soon. I think it's worth it to spend that extra time to make a different video because it is a pretty complicated topic. So I'll do that on a separate video for y'all, so be looking out for that. And then from 5 on, is really just doing practice problems. So that is both chapter 11 practice problems and then review of ochem 1 practice problems. So predict the products of the following reaction. So this is a peroxy acid. It looks like a carboxylic acid where they like just added an extra oxygen to it. And what that does is add an epoxide right there on the double bond, right? So you get rid of the double bond and you add an epoxide there. So I'm just showing you where it goes, but it will end up looking like this. And then that's the first step. The second step, you have a base that's going to attack. So I'm going to walk through the mechanism of this in the other video, but a little short overview of the mechanism is if you have a strong nucleophile or like a basic environment where it's negative, it's going to attack the least substituted side for an asymmetrical ether. So you have 1 or 2, right? Option 1 or option 2. The nucleophile is going to attack at option 2 because it's the least substituted side in this case. And I know it's basic because it's going to do, because it's got this negative charge. So basic least, acid would do the most substituted side. And then you already have 4 bonds to this carbon, right? There's a hydrogen and an implied hydrogen here and here. So adding another bond isn't going to work. So a bond has to break for that to happen. So that ring opens. That's why it's called a ring opening of epoxide. So this, I always number actually because I always lose them. My carbons, 1, 2, 3. That's a hydrogen, but I'll just draw over it 4. So 1, 2, 3, 4. So 4, carbon 4 is where, you can kind of see my handwriting's pretty small. 4 is where the oxygen attacked. So there's a new bond that forms from 4 to that oxygen, and then it comes with the ethyl group, the CH2CH3. But at 3, the bond broke between 4 and the oxygen, but 3 still has this oxygen with a minus charge. Now, if you had an H plus after this is step 3, you could turn this into an alcohol, OH, and then you have your O, 1, 2, 3, 4. And that would be your final, but because there's no H plus, technically that last step doesn't actually happen. Okay, sorry, that lighting was driving me crazy. Maybe this lighting will be better. I don't know what the deal is. I usually do the videos at this desk, but we just slightly rearranged it. So, okay, there we go. Okay, the next one is what's called an alkoxy mercuration demercuration. So if you remember oxymercuration, demercuration, it adds an alcohol to the more substituted side because it's Markov-Nikov, or an OH to the more substituted side and a hydrogen to the less substituted side. But normally for oxymercuration, demercuration, that's water right there. But in this case, because it's an alcohol, that's actually going to be what adds to the more substituted side. So just from knowing that, I know a hydrogen is going to get added here. And then instead of an OH being added on the more substituted side, OCH3 will be added there. So you really need to remember oxymercuration, demercuration rules to know why it adds like that. You don't have to know the mechanism. It just goes through like that triangle forms, and then the alcohol comes and attacks on the more substituted side because it's partially positive over there. If you remember all that, great. If not, it's okay, as long as you know that it adds the more substituted side because it follows Markov-Nikov's rule. Okay, the next one is turning alcohol into a good leaving group. So here's a reaction we can do with an alcohol that I forgot to add in. This is actually a mesyl chloride. So you can put MESCl or MECl. But a lot of times what I'll actually just do is make this a good leaving group. Basically, it just replaces your alcohol with a good leaving group, and it retains stereochemistry. So I'll just replace OH with the word leaving group because alcohol by itself isn't a good leaving group. It has to be protonated to be a good leaving group. So now that it's a mesyl, it's a good leaving group. If you're doing this on a test, you do need to write ME on there or OME or whatever just to make sure that it's right for your mechanism. But to make it easier for myself in multiple choice questions, will do it like this. So then the leaving group will leave. Hope that's a hydrogen. and you form a carbocation, but one thing we always have to look out for when there's a carbocation in SN1 and E1 reactions is rearrangement. Is there a more stable option nearby? And in this case, there is. This carbocation is secondary, this one is tertiary. And tertiary carbocations are going to be happier. So you'll have a hydride shift. So now this hydrogen will shift over here, and you'll have two hydrogens. Stereochemistry doesn't need to be drawn because they're the same, so it's no longer a chiral center. This methyl over here, because it's a carbocation, it doesn't need stereochemistry either because carbocations are flat. Remember, they like flatten out, and then your nucleophile can attack from either side. So that's the first step. And then this alcohol comes in and attacks. I guess let me back up a little and say, we know that our first step right here is just replacing the alcohol with the tosyl chloride or the mesyl chloride to make it a good leaving group. And after that, I knew it was going to be an SN1 reaction because there's no heat. It's not a bulky nucleophile, so it can't be E1. And there's not a strong nucleophile, so it can't be SN2 or E2. So the only thing left is for it to be an SN1. And the first step in an SN1 reaction is your good leaving group leaves. So that's how I got there. I should have probably explained that further on. And I'm not going to draw stereochemistry here because you get both. You would get both this being a wedge and a dash, but also it's technically got a plane of symmetry right through the middle, so it's not a chiral molecule. These two attachments are the same, so I'm not going to draw the stereochemistry out. Okay, now the next one, this might be kind of tricky, but whenever I see a double bond like this and an alcohol in the presence of acid, I usually think protecting group. And another thing you can think is addition reaction. So if you have H plus and a double bond, you've seen that double bond attack the H plus and become a carbocation, and then a nucleophile come in and add as an addition reaction before acid catalyzed hydration. It's the opposite of acid catalyzed dehydration. So if your nucleophile comes in and attacks, you have your O and then CH2, 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 CH3. There is your hydrogen still on there, so this is initially positive, but it will get deprotonated to make this. So whenever I'm looking at a reaction, I'm trying to decide what reaction is going to take place. Like on this one, does this look like an acid-base reaction? No, because it does have an acid, but neither of these are really super strong bases, right? And then I asked myself, well, is it something we learned in chapter 6, substitution, elimination reaction? It doesn't look like it because there's not a good leaving group anywhere, so I don't think it would be a substitution or elimination reaction. So then I get into chapter 8, and I'm like, is this something we learned with alkenes? Is this an addition reaction? And we have an alkene and we have an acid. And that's where the light bulb goes on for me. Like, oh, we have an alkene, we have an acid. So we could add that there and get the carbocation, and then we have something that could attack the carbocation once we have it. So that's how I narrowed it down to be this type of reaction. Okay, now for E, I'm looking at this alcohol, and the first question I always ask is this an acid or a base? Well, NaH is the same thing as H minus, right? H minus, sodium plus. So if that's true, then it is an acid-base reaction because alcohol is relatively acidic. You have this hydrogen that's pK is like 16 to 18. So in that range, if it's 16 to 18, then this is going to deprotonate it, and you end up with O minus. So that's the first step. And then once you have that, you add in this Br and this alkyl bromide. So if you have this and this, now you have to go through the whole thing again. Is this an acid-base reaction? No, there's not really an acid anymore with our nucleophile. Is it substitution or elimination? Well, we have a strong nucleophile. It's a negative, so we know it's strong. And we have a good leaving group. So actually, yes, this looks like an SN2 reaction to me because the nucleophile is strong and this is primary. It's not too bulky at the front end here. So I think this would be an SN2 reaction. So you end up with O. I don't know why I said O. You end up with this structure, which is actually an ether. So technically, this is actually a Williamson ether synthesis by an SN2 reaction. Okay. Which reagents would you use to accomplish the following transformation? So whenever I see a double bond, I go through the same kind of questions that I asked. Is this an acid-base reaction? Well, if you add acid to a double bond, it would maybe act on it like addition style. That's more of an addition reaction. So no, I don't think that could be an acid base because there's not just a transfer of a hydrogen. That's what acid bases are. Then is this a substitution or elimination? Well, elimination ends up as a double bond, so I don't think if we're going from a double bond to something else, that would be an elimination. And substitutions just swap something out. But this is actually adding something to my double bond. So this is an addition reaction. So that must mean it's chapter 8, addition to alkene. So we learned a few addition reactions. We learned acid catalyzed, hydration, hydroboration oxidation, and we learned oxymercuration, demercuration. And acid catalyzed and oxymercuration both add the alcohol to the more substituted side. So this would be more substituted because that's where the carbocation would form. So that's why for acid catalyzed, oxymercuration, demercuration also follows that same rule. So the only thing we could use for this would be hydroboration oxidation. So that's NaBH4. I think what's the other thing I have? Let me check my notes real quick. I can never remember. Oh, not NaBH4. That's a reducing agent. I'm getting myself mixed up. It's BH3THF. I don't know what. My brain was just thinking about class today, I guess. And then H2O2 and NaOH. So that's hydroboration oxidation, and that adds anti-Markovnikov, where the alcohol goes to the less substituted side. Okay, now I'm looking at this one and I go through the whole chain of events again. Is this an acid-base reaction? Well, this isn't just transferring a proton, so I'd say no. So is this a substitution or elimination? Well, eliminations end up with a double bond, so I'd say no. But this does look like it's substituting something out. So it does look like a substitution reaction to me. So I think you could make this an SN2 reaction with just OH minus as your nucleophile. It would come in an attack and kick this out. Now, I know Dr. Corrales decided to make it a little bit more complicated in the key that they made, so you could do a different approach. And there's many different approaches you could probably do, whatever makes sense to you, but this was the first thing I saw. A different thing you could do is do an elimination reaction, like an E2 reaction. So you could have like tert butoxide and heat and make this a double bond. And then add same thing, BH3THF, so it goes to the more the less substituted side, hydroboration oxidation, and then you could add an alcohol out here. So whichever of those makes sense to you, whatever you see first, both of those would be considered correct. Like you wouldn't get one wrong because you did it a specific way. So you can do it either of those and you will get it right, whatever makes the most sense to you. This is when ochem kind of starts to diverge. Like there's not just one answer, there's multiple right answers. Okay, so now we're going back into more of ochem 1. So I look at this question. I know it's not an acid base because there's no base. I know it's not a substitution or elimination because there's no leaving group or nucleophile. I know it's not an addition reaction because we don't start with double bonds. So then that brings me to chapter 10, which is radical reactions. And if I see bromine with a radical, or with this H nu, then I know a radical forms. So the Br forms a radical. And then it's going to steal a hydrogen to leave behind a radical. But there's still another bromine radical floating around, so then it'll come in and form a bond with the bromine. I know the mechanism, so it's easy for me to predict, but if you don't know the mechanism, the radical forms at the most stable position, which is the same as carbocation, so tertiary or secondary, whichever is the more stable, or whichever you have, and then the bromine will just go right there. So that's this reaction. All you do is add the bromine. Now, HBr in the past, well, I'll start at the beginning. This isn't an acid-base reaction. We have the HBr as an acid, but we don't have a good base. We have the no substitution or elimination because there's not a good leaving group. So then it must be addition reaction. So if it's an addition reaction, in the past we've had the double bond attack the H, and you get a carbocation. But this isn't a regular addition reaction. It's in the presence of peroxide. So it actually goes through a similar mechanism as we mentioned up here, and it causes an anti-Markovnikov addition. So actually, the radical forms at the more stable position, and that's where the hydrogen goes in the end. So instead of what you normally expect, the Markovnikov formation, you get the opposite. So normally you'd expect, if you had this with HBr, this is not in the presence of peroxide, what I'm drawing you. Like normally what we learned in chapter 8, then there's a positive charge here plus Br minus, and then the Br minus will come and attack, and you'd get this. But when you have it in the presence of peroxides, a radical mechanism occurs instead, and I'm not going to go through the whole radical mechanism with you. You can go look at my chapter 10 practice problems if you want to see that, but just know that instead the Br adds Markovnikov, or anti-Markovnikov. So this is Markovnikov, no peroxides. In the presence of peroxides, it adds anti-Markovnikov, where the Br goes to the less substituted side. Okay, now for C. We have go through the same process. Is this an acid base? There's not a hydrogen that seems like it's going to move around. There's not a good acid or a good base. So then the next question I ask is this substitution or elimination? And there is a good leaving group, and there is a strong nucleophile, so I think this is substitution or elimination. So to decide if it's SN1, SN2, E1, or E2, I ask myself, is the nucleophile negative or positive? Well, OET is negative. It just has the Na plus as a counterion. So it's a negative. And then, so it's a strong nucleophile. And then heat makes me think it's elimination. So E2. And if you're confused on how I did that, I make this whole chart where I go like, oh, if the nucleophile is strong, it's going to go to 2. If it's weak, it's going to go to 1. And then there's factors that make it go E2 versus SN2. I have a whole video on that and a short video on TikTok that you can check out. But for now, I'm just going to say I came to the conclusion that it was E2 using that chart. It was strong, and because there's heat, it favors E2. So the other thing you have to think about with E2 is that is the hydrogen that's leaving anti-periplanar to the leaving group. So when you have it in something that can freely rotate, like a single bond, you can do it in Newman projection, but this is in a cyclohexane. So you have to put the ring into a chair conformation and then determine if it's axial or equatorial. And the leaving group and the hydrogen have to both be axial. So I'm going to make this leaving group axial, which means that the hydrogen adjacent to it would be equatorial. So if this is axial, the bromine is axial, this hydrogen is equatorial, and the CH3 is axial. So actually, you can't even consider Hoffman versus Zaitsev product because there's not a hydrogen that is coaxial. You're going to have to take from these two hydrogens. So these hydrogens on the left side will be taken because you need that coaxial. So we talked about that a lot in chapter 7. So go back and review that if you need to, but basically you just have to make sure when you're having an E2 reaction that'll have a coaxial hydrogen. So in this case, your OET minus is going to come in and steal that axial hydrogen. The electrons will fill in and make a double bond, and the bromine will leave. And you'll end up getting something like this. That was kind of a lot, I know, but if you can go back and review chapter 7 to figure out why it needs to be anti-periplanar or anti-coplanar in an E2, it just has to do with like the backside attack and the way the nucleophile takes it. Okay. Now, next, let's see, terbutoxide. So again, if I'm like, is this acid base? Well, this could be a base, but there's not an acid. So then substitution elimination. Well, this is a strong nucleophile and this is a good leaving group. So that tells me that this is going to be a substitution or elimination. And it's a strong nucleophile. So again, I think it's going to go to the 2 side. And it's a big bulky base. So again, I think it's going to be E2. So you don't need heat to go to E2. You just need either a bulky base or heat. So we have to consider 2 things whenever we're doing that. We have to consider if it's Zaitsev or Hoffman. So Zaitsev is the more stable internal. Will it take this hydrogen or this hydrogen? You have 2 options. And then the other thing we have to consider is there one that's anti-coplanar. So if it was more narrow, it would take the internal and give you, I always remember Zaitsev, more stable, smaller nucleophile, gives you that double bond there. But because it's Hoffman, it's going to go from here. And that means all 3 of these are hydrogens. So at any point, any of them will be in the anti-coplanar position, so we don't have to draw out our Newman projection. So this just comes in, attacks, the leaving group leaves, and you end up with this structure. Okay, so that's a quick review of some of the big ideas from chapter 7. Okay, here's another HBr, but this time there's no peroxide, so the double bond will attack the HBr, and that bond will break. So the H will add out here, and then you'll get a positive charge right there, and then the Br minus that was formed when this bond breaks will come in and attack, and you'll get the bromine. That hydrogen is still over there, but I just didn't draw it in because it's an implied hydrogen. Now, if there was peroxides, the bromine would add out here. So if there was peroxides, you'd get the opposite product that would look like this. So that's the anti-mark with peroxides. Okay, this next one. So again, it's not acid-base. There's no acid or base, really. It's not substitution or elimination because there's no good leaving group. So that leaves us with addition reactions from chapter 8. So this looks like, to me, an addition reaction that will do the formation of a halohydrin. So normally if you just have Br2 with an alkene, the bromine will add on either side. But in this case, you have Br2 in the presence of an alcohol, which means you're going to get bromine on one side and an alcohol on the other. And it actually does add the bromine first. Then the alcohol comes in and attacks Markovnikov style. So the bromine will be in the position the hydrogen's normally in, and the alcohol will add to the more substituted side. So I'm not going to go through the whole mechanism. I mean, briefly, I can show you that essentially the nucleophile attacks the Br2, and that crazy triangle situation is formed with the bromine still on there. And then, that bromine departs. But instead of the bromine attacking, there's so much alcohol in this solvent that the alcohol can actually come in and attack right there and kick out this bromine. So you get the OCH2, CH3, and it's technically still protonated at first, but it gets deprotonated. And then over here, you have the bromine that's still attached when the bond breaks. So that's a very quick overview of the mechanism, but as long as you kind of have a good idea of the mechanism, you should be fine on that reaction. So you'll end up with a structure like this. Oh, and there is a methyl still there from originally. So that's the formation of a halohydrin. That's also chapter 8. And this is actually also chapter 8. And I love this reaction, osmium oxide, because it basically just cleaves this double bond and makes adds an alcohol to each side of it. So cold KMNO4 does the same thing. If you have hot KMNO4, it'll cleave all the way, but it cleaves, I guess, just one of the 2 double bonds is a better way to think about it. And adds 2 alcohols, and it adds them in a syn fashion. So you get the addition of 2 alcohols with osmium oxide, and that's it. That's all it does. It just adds diols. Now this reaction is again from chapter 8. This is another addition reaction. There's no acid base. There's no substitution or elimination because there's not got a leaving group. So all that happens is you add HBr, you add it and the bond breaks just exactly the way we did before. But now it forms a carbocation and the hydrogen adds on this side. Then the Br minus that was formed in that first step will come in and attack, and you get Br with your double bond. And there is that hydrogen still there, but it's implied, so I'm not going to do anything with that. But because you have excess HBr, it actually happens again. And you get your hydrogen adds out here, and you have your Br. There's a carbocation, and the Br minus that was formed in this step comes in and attacks, and you just add 2 bromines. I've gone way down into this areas, so my bad. But yeah, that's the whole reaction is you just add 2 bromines, and you do that according to Markovnikov because the carbocation needs to go to the more stable side. Okay, this next one is just like osmium oxide with cold KMNO4. It'll cleave the one of the 2 double bonds. I drew it better this time where it's only cleaving one instead of both. And it adds 2 alcohols, and it does add them in a syn manner. So they will still both be wedges or both be dashes. Either one, it doesn't matter. And there is still a hydrogen here, 2 hydrogens, but they're implied, so we don't draw them out. Now ozone, and I have KMNO4 and osmium oxide when I see them with double bonds. I just have it memorized, so I don't have to go through the whole thing. But you can go through the whole thing, and eventually you should get to double bond and realize this should be some type of addition reaction or cleaving the double bond. But what O3 does is fully cleaves the double bond and adds an oxygen on each side. So your final product is an oxygen there and an oxygen on this side. And if this was a stronger oxidizing agent like KMNO4, it would oxidize these even more, and we'll see that down here. So this is the same reaction with hot KMNO4. It adds an oxygen to each side. But as you've seen in class, now that we've covered oxidizing agents, KMNO4 will reduce or will further oxidize aldehydes, right? So this KMNO4 will actually oxidize this even more to where you'll get an OH. And then we haven't talked about this in class yet, but if you have carboxylic acid with a hydrogen on the other side in the presence of presence of KMNO4, it will actually further oxidize this to CO2 plus. I think this departs as I think you might have water as well as a side product. So you end up with this and then the fully oxidized formaldehyde to get CO2. Okay. Now our last one. So I look at this. Is this an acid-base reaction? I guess this OH could be protonated. So that would be a type of acid-base reaction. But then we just end up with OH2 plus, and we're still in the presence of water and heat. So then what happens next? Is this acid base further? Well, we already had acid base. So next question, is this substitution or elimination? Well, water, protonated alcohol, is a good leaving group. So I'm going to say that the good leaving group in the presence of a weak nucleophile and heat, this is an E1 reaction. So this leaving group will leave, and you'll get a carbocation, and then rearrangement will take place so that you have the most stable carbocation possible. You actually get a methyl shift there. And then the water that's present in the solution will come and steal this hydrogen. The electrons will be left behind, and you'll form a double bond right there. So this is oh man, I was off the page. Sorry. So the water steals one of these hydrogens. The electrons that were in the bond between the hydrogen and the ring get left behind right here to form your double bond, and that's how you get this final structure. So one thing about this is that this is an elimination reaction. First step is acid-base to protonate and make it a good leaving group, and then you have an elimination reaction. But it has a special name called acid-catalyzed dehydration. So you can just be aware of that. Okay, and then this next reaction will do the same thing. Is this substitution, or is this acid base? Not really. Is this substitution or elimination? Well, actually, this is a special type of elimination reaction that we learned that will occur twice. I think we learned this in chapter 8. It doesn't matter which one goes first, but it'll take the hydrogen and one of the bromines, and then it does it again because there's 2 equivalents. So it takes that hydrogen, the electrons go there, the bromine leaves, and you get a carbon-carbon triple bond. So it basically does 2 eliminations in a row. I realized I drew the wrong bromine had departed, but it doesn't matter either way. It'll kick out a hydrogen and bromine and a hydrogen and bromine to end up in a triple bond. Okay, so that's an overview of our group work, and I will be doing a video with the mechanism for opening of epoxides here shortly. I hope that's helpful for you, and if you have any questions, feel free to let me know.